Well, thanks to the organizers for the invitation, and I guess I'll start with the apology for being the perhaps the biggest misfit for the program, because I'm not going to talk about counting. So I guess I have, it's April Fool's Day, so I guess I fooled the organizers. But it's hopefully not too disconnected from some time level from the main theme of the workshop, because I won't talk about counting, but I'll talk about optimization, but it's related to complexity. Not NP type complexity, because we are too far from there for the types of problems I'm interested. And the classification, in some sense, will show up. It would be nice to classify problems that I'm about to describe. In 2 words, we will look at the random instances of constraint satisfaction problems where you want to solve some optimization problem. So many such problems exhibit an apparent gap between what can be achieved algorithmically and what can be established by existential results. So there's many examples of such problems, but if you have like a k-set, a random k-set, coloring of a random graph, maximum independent set of a random graph, but you haven't seen any of such problems before, no worries. Next slide, I will introduce one of the vanilla versions of this problem. And the sort of the main theme is that because the problems have random instances, sometimes without finding the optimal solution, you can say what's the optimal solution. You can just do some kind of a probabilistic analysis and say that the optimal largest independent set is this. But then you want to find it, actually, and that's where the interesting things begin. So what is the source of this apparent hardness? That's we would like to understand, perhaps classify. That would be nice. And one of the things that seems to be hindering the progress and sort of creating the obstacle is a certain property. For the lack of a better word, I'll call it the overlap gap property, that, or sometimes referred to as clustering property, shattering property, that really originates in the theory of spin glasses in statistical physics, but I will not go, you don't need to know anything about statistical physics for the purposes of this talk. And what I will do today is I will give an illustration of this problem for the so-called maximum submatrix problem. It's a very simple problem to introduce and describe. But I think what's interesting about this problem is it's not a vanilla constraint satisfaction problem. There's no constraints. It's of a different nature. It's actually over continuous variables and so on. Yet you see the same phenomena that you see before in this class of problems, typically on sparse random graphs. Okay. So after about my third slide, I'll focus on this concrete problem and walk you through. But before I do that, let me introduce one of such problems, and arguably this is the most embarrassing algorithmic problem in the theory of random graphs. So here's the problem. It's actually very old. Consider an Erdős-Rényi random graph with parameters with n nodes and edge probability p. So I hope everybody is familiar with that, but just to remind you or tell you what it is, so we have n node graph, and every edge is present with probability p and absent with probability 1 minus p independently, right? It's a vanilla Erdős-Rényi graph going back to 1960s. In this graph, we consider the largest clique. Again, clique is something that all of you or perhaps know. It's a fully connected subgraph. You want to find the largest such thing. We don't counting. We just look at the largest object. So largest clique, fully connected graph. It's actually fairly easy to show that it has this size, twice log n, with the base 1 over pp is the probability of an edge. And this is one of the simplest applications of the probabilistic method. You just do the expectation counting, and you show non-constructively. You can show that the largest clique has that size. Okay. Well, what about the algorithms? There is a trivial algorithm, greedy algorithm, that finds a clique of size half of that. To be honest, call it this algorithm greedy, or even calling it an algorithm is giving it too much credit, because this is the dumbest algorithm one can imagine. It works like this. You pick a node, you look at all nodes connected to this node, and you discard everything else. Then, among all those nodes which are connected to the starting node, you pick any other node, and you look at all the connections to this node and discard everything else, and then you repeat, and then you get your answer. So this is the dumbest algorithm one can imagine, because you're hardly doing any serious exploration of your graph. You're not looking at the maximum degree, you're not doing semi-definite generalization, you're not doing any of this machinery that you don't need any of that. It's speaking of doing nothing, this is almost worse than this is doing something stupid, yet it gives you this. But the intriguing thing is that no one was able to improve that. And that goes back to Karp's problem, 40 years old now, of the challenge of finding a better algorithm. Can you, for example, construct 1 plus epsilon times log n clique? And nobody was able to do that thus far. And that's very embarrassing, because the transition from triviality to a challenge is immediate, right? So there's no middle land where you can say, okay, I can at least do that much, but not better than that. Incidentally, after that, lately there's been a lot of progress on this version of this problem called the hidden clique problem. The hidden clique problem is much later. It was proposed in the 1990s. In fact, it's motivated by this problem. So this is one of the oldest and the most embarrassing problem in the theory of random graphs and algorithms. It's still open, still embarrassing. Just to illustrate this sort of stability of that kind of challenge, it's the same story pretty much in a sparse random graph. So in sparse random graph, all we do is we change the probability p. So instead of p being constant, it's of the order constant divided by n. So d is constant. Every edge is selected with probability d over n. In this case, you can find, again, existentially largest independent set, and you can write down that asymptotically what it is. It is linear in the number of nodes, so the graph is sparse. Independent set is linear in n, and you can find the prefactor asymptotically. It's twice log of d divided by d. D here is actually the average degree of this graph. All right, so existentially we know that. You can use the same but naive greedy algorithm, and it will give you only half of that. And again, nobody was able to improve it. Okay, that's the and that's a similar. And there is a similar story for many other problems that I've listed in the first slide. Now I want to switch to the problem that I would like to discuss today, but before, let me stop and see, do you have any questions about historical kind of background here? Okay. So here's the problem that I would like to consider today. It is the problem of finding the largest, in average sense, submatrix of a Gaussian matrix. The problem is very simple to state. We have an n by n matrix with IID standard normal entries. Why normal? Almost for historical reasons, because people have looked at that before, so we've decided to look at it. But you can replace it with other distributions and study it at your leisure and see if similar things show up. You have a fixed parameter k. I want you to think of k as very small. It's interesting cases where k is constant, or I don't know, log n, up to log n. This is where the story evolves. You have a fixed parameter, you have parameter k, and you search for the case by case submatrices, not principal, not contiguous. It's sort of written as contiguous, but it's not really, doesn't need to be contiguous. Largest submatrix, largest in the sense of the average entry, or the sum of entries, but I'll stick with the average for concreteness. So your goal is say something about such a largest average entry among all submatrices, and hopefully also find it algorithmically. Okay, is the problem clear? Okay. So this paper has been studied, but relatively recent. It's not as old as largest clique problem, although one can sense a certain connection between the two. So a fairly recent paper by Bamidi, Day, and Nobel showed that actually the largest average entry that you can achieve has this very simple expression, square root 4 log n divided by k. The proof is not terribly complicated. They do actually much more than that. But if you just wanted to get this, you essentially use the same tool as for the largest clique. It's a moment argument. You compute the expected number of submatrices achieving a certain value. It's all Gaussian, so tails are easy to handle. And then you show that there is a concentration around this expectation, and then things are good. The asymptotics here is it's non-mysterious. Let me give you intuition. It's written here, but you don't need to follow this. Let me just say it in words, what this asymptotics is. What it is that if you have n IID standard normals, we know what the maximum is. It's standard deviation times 2 square root times square root 2 log n. Okay, so we know what's the largest of n IID Gaussian is. Okay, now our matrices, averages of matrices, and we have n choose k square of them, the number of choices of submatrices, n choose k square. Each average for the fixed matrix is a Gaussian with a variance 1 over k squared. Okay. Now what you do is that pretend that they're all independent. Of course they are not, because they overlap, right? So they have the correlations. But pretend they're independent. And look at this asymptotics as if they were independent. And when you do, you recover this. So it's basically saying that this dependence is irrelevant. It's the supremum of essentially largest of that many Gaussians with this distribution. But of course you have to overcome these correlations, but you do that with the moment argument. What about the algorithms? So incidentally, quick side remark is that problem came up from applications. In the bioinformatics specifically, where the people have looked at so let me go back to the matrix. The matrix actually of interest is non-square matrix, but you can define it for non-square matrix as well. And in bioinformatics, you're interested in, okay, the rows corresponds to patients and the columns correspond to genome expression, and dense submatrix presumably correspond to areas of problems. For example, genes that express the presence of cancer for those patients that are part of that group. All right? So it has applications, but I don't know, frankly, much about this application, so I'll skip that. Now, obviously, the problem has some algorithmic challenge to that, because the number of choices is large. Even if k is constant, like 10, it's admittedly polynomial time, but n to the 20, what good is it? And in this paper, in the applications paper, a very natural heuristic was proposed called the iterative search procedure. And it's a very simple and reasonable construction, the algorithm that, let me describe it. I have a slide describing this algorithm formally, but it's not very parsable, so let me just do it on the board. I think it would be easier. So what you do is the following. So you want to find the largest submatrix. You fix any of the k rows, for example, the first k rows here, without loss of generality, and then find the best matrix within those k rows only. Now that's easy to do, because all you need to do is find the largest column with the largest sum of entries, and the next column with the largest sum of entries, and the next column with the largest sum of entries. Again, they don't need to be contiguous, but for my drawing, ease of drawing, let's pretend they are. So you found the best matrix here. Incidentally, the asymptotics of this restricted largest submatrix, which is now trivial to find, is 2 log n divided by k, versus the globally optimum is 2 outside of the root. So this is global. When you do it restricted version, you find here, but that you don't stop here. What you do, the next step is that, okay, now you restrict within columns, and you find the best submatrix within those columns. And then you find, you restrict those, within those rows, you find the best submatrix within these rows could overlap with the previous choices. It's actually likely to overlap. And then you keep iterating. For example, you do something like this, and then you do something like this, and so on and so forth. That's iterative search procedure, very natural heuristics to try to do something here. Any questions? Okay. What in the paper that established the global optimality here by Mediday and Nobel, they wanted to say something about the performance of this algorithm, iterative search procedure, but that's turned out to be challenging. That's not obvious to do because now the dependencies actually mess it up. Things become complicated. So instead, they did something different. They gave an evidence that indeed what you get in the first iteration is pretty much the best you can do. So this is the best. What they did is they showed the following. Notice that you iterate here and here. At some point, you stop. And when you stop, that matrix is optimal within the set of rows and within the set of columns. Because otherwise, you would be able to improve. Right? So then they said, okay, let's look at all such matrices which are locally optimal. Though locally means within rows, within columns. And let's look at all such matrices. And what they found is that with high probability, almost all of them have this value, which is square root 2 smaller than the global optimal. And that gave, that suggested that in fact that's the performance of this algorithm. Okay. And that's the intuition. All right. So some open questions. What is indeed the true performance of this algorithm? Are there better algorithms? If we get to the optimality, global optimality, hooray, great for us. But if we stop short, what's hindering it? So what's the obstacle for this apparent computational complexity? Sasha?
Is it clear that it converges fast, or you just stop it when you see no big improvement?
It is clear that it converges, that whether it converges fast, that's not guaranteed. It can.
No, it will stop eventually. But
yeah.
Do you just stop when you don't see significant improvement, or?
Right. So the answer to this question depends empirical testing of the algorithm versus the actual analysis. As far as the analysis is concerned, I'll give you the full answer. As far as the empirical answers are concerned, is that it's when people tried it on real data, with real bioinformatics data, they were finding that it's actually not easy to find something really good. I mean, they don't know it's optimal or not, but they start from one position, optimize and get something. They start somewhere else and get something else. So even the empirical data suggests that even empirically this problem is hard. Now you can do all kinds of thresholding rule that if I don't improve by more than something that I stop, you can do any hacks you want. And that's sort of user dependent. As far as the performance, the provable performance of this algorithm, that's one of the results, and I'll describe it shortly.
So they ran it to the end, right?
In the empirical, I'm not sure. I don't.
The matrix produced by this algorithm, that means that you really.
I mean it literally produced by this, algorithm until it gets stuck somewhere. Global optimality or globally optimal or somewhere in before.
Yeah.
Yes.
Just if I understand it correctly, I thought that maybe I understood it wrongly, that all the local optima behave more or less the same.
Majority, yes.
Majority.
Yes.
So then, doesn't it suggest that exactly the algorithm has not stopped in the end?
Good. So not technically, because, okay, what you know is that, like, say, 99% of the locally optimum gives this value. But maybe this algorithm is clever enough that somehow it overcomes that and sort of wiggles its way into something higher.
Okay.
So that's what you want to rule out.
Okay.
All right, so let me introduce another algorithm. And given that this problem is so, in a way, simple, is in a way related to the graph problem, let me actually turn it into the graph problem. So the way we're going to turn it is very simple, thresholding idea. We fix the threshold theta, and every time we have an entry greater than theta, we put 1, and every time we have an entry less than theta, we put 0. Right? So now instead of Gaussian entries, we have 0, 1 entries. Now think of this as an adjacency matrix of a bipartite Erdős-Renyi graph. Bipartite because my original matrix was not symmetric, and therefore this matrix is not symmetric. If you like symmetry, you can start with the original problem being symmetric. You will run into the same issues, rest assured. But we start with non-symmetric, fine. So it's a bipartite random Erdős-Renyi graph. The edge probability is just the probability that the entry is at least theta. Okay. Now what you can do is the following. Okay, granted we can't solve the clique problem on the Erdős-Renyi graph, but we have a greedy algorithm that does half of that. If you apply this half simple algorithm for bipartite graph, it gives the same performance. It's log n divided by, it's log n essentially with the right base, as opposed to twice log n. But that we can do because greedy algorithm gives that. So we found the clique of size m for of size m, where m depends on p, but p now is a function of the threshold. We cannot live with any m here. So what's the implication of that? Is that for such a matrix in a clique, every entry is at least theta. So not just the average is theta, at least theta. Minimum entry is at least theta. So we're doing better in some sense. But you have to be careful. You have to select theta not too large so that your clique is of the right size. It has to be k by k. Otherwise, you're not solving the right problem. Because we have a target matrix that we want to produce. And so now you can solve the reverse engineering problem. Set theta large enough so that this is still at least k, and see what it gives you. So I guess I'll keep it as a suspense, sort of. It's actually it's easy to reverse engineer, but I'll wait for one slide before I tell you the answer. Let me start with the previous problem. So now I introduced two algorithms. One was this iterative search. One was this connection based on the cliques in the random graphs. Some results. First result is that, indeed, no surprises. Iterative search procedure will not overcome the local barrier. It will actually produce the clique of that, a matrix of that size. So this local computation by Bamidi et al. Was the right computation. This result is technically in the paper is the most involved and least interesting in a way, because all we do in the end, after 20 pages of extremely painful computations and so on, in the end there's no surprise. What you expected, that's what you get. I think surprising results come perhaps nicely. All the surprises are actually simple to derive, and hopefully some of the things you will find surprising. Okay. So fine. So this is this, and now one thing I forgot to. Oh no, I didn't forget to mention. It turns out that the number of operations is actually constant with high probability. So that's to Sasha's question. You can prove that with all. In fact, it's bounded by geometry. The probability that you will run more than 10 steps is rho to the 10. All right, and that's literally no thresholding. Literally, you get stuck. No improvement after that 10. Iterations. Here's the second, for the second thing. You optimize over threshold theta and solve the clique problem and try to get however large matrix you can get. And it gives you the same answer. So it's optimized over theta, clique theta, which maximizes, which sort of solves the right threshold problem. So maximum theta such that you still get k by k clique. That theta has the same value. A little bit upshot here is that instead of the average value, you get the minimum value here, but it's marginal. Okay, so in light of this, one kind of perhaps time to pause and think, maybe this threshold, by drawing an analogy with cliques in the random graphs, maybe this threshold is kind of like half log n versus 2 log n threshold for greedy algorithms versus truth in random graphs, right? So maybe overcoming this threshold is hard, as it was 40 years old hard for the cliques in random graphs. And that was sort of our belief at that stage. But then, surprisingly, we found that, in fact, there is a better algorithm, and a very simple better algorithm. We're not terribly creative in giving it names, so we'll just call it sequential greedy algorithm. And that algorithm that I'm about to describe, it's very simple, and I'll describe it shortly. And in fact, the analysis is also simple, gives 4/3 better than the previous two algorithms. So now, to keep things in the relative sense, so I'll put 1 here, and this 1 represents 2 log n over k. That's the performance of the original 2 algorithms. Now, square root 2 here, that's global optimum. That's where you want to get. That's a holy grail in a way. So this algorithm gets you 4/3, which incidentally is 1.33 something, and root 2 is 1.41. So you could say that, okay, it's not too bad, we're almost there, a few digits apart. But of course, these numbers are in a way meaningless. Now let me describe the algorithm. I don't think I have a slide for that. I would like to do that. Oh, yeah, I have a slide for that, but let me do it on the board. The algorithm is actually very simple. What you do is you pick just 1 row, any of the rows that you like, and find the largest. So this is the largest entry. Just 1. And then you look at this column, and you find the largest entry in this column. If it happens to be the same one, which is actually unlikely. Actually, not that unlikely, because it's the largest of... Anyways, if it's the same, then find the next largest. If it's not the same, good. So you have 2 entries now. So you have 2 by 1 matrix. Fix this row. And in these 2 rows, find the next best 2 elements. So 2 elements which have the largest sum, different from this one. So you have a 2 by 2 matrix now. Fine. And then now you have 2 rows. Find the next 2 by 2 entries in the 2 columns. So you have 2 by 3 matrix. And then now you get the picture. And this find next best 3 by 3 column. And keep iterating until you get to the k by k target size. That's the algorithm. And this algorithm is actually fairly easy to analyze. I have a proof sketch here, but let me say in words what's the idea of the proof. You don't need to follow details here. The idea is that every time in step T, you add a row of entries which are Gaussian and they have the extreme property. So this is a row which has the largest sum of entries in these T columns. And then you use the extreme value of the IID Gaussians and plug the value. And when you do the summation, then becomes like an integral, because now you have extreme value of T by n Gaussians gives you something like this. Then you integrate square root, and then you get 4/3 because it's an integral of the of square root T from 1 to k, and there is an extra factor here. So that's the details. Now, when you do this analysis, you have to be a little bit careful because there is a dependency here. But what we do is that we split the matrices into chunks and then sort of only use for the best within the chunk, and then you guarantee independence, and turns out it doesn't hurt you too much. All right, so we can do 4/3. So far we can do 1.41. This is the interesting region. We want to say something about that. So unless there are any questions? Yes?
When you did your thresholding, and got that 0-1 matrix,
Yes.
what's the value you get if you leave the values of the entries in? Because they must be distributed on theta infinity, so it must improve that.
Unfortunately, it doesn't improve because the value of theta is already 2 log n over k. It's concentrated, it's lower order magnitude improvement.
So you don't get any...
And obviously, quote unquote, obviously, it's about this algorithm. If you try this algorithm for the click problem, hoping to beat log and threshold, you fail. So there's no improvement there. It would be amazing that some simple hack like this would actually get you there. But it gives you something in the Gaussian case. Any other questions? All right. So what is the... okay, granted we managed to improve from 1, quote-unquote, so from the sort of default algorithms by 4/3, we couldn't do improve. And simple hacks like perhaps adding 2 columns or 3 columns at a time don't give you improvement. So now let me switch gears and talk about perhaps there is indeed some kind of a phase transition indicating the hardness of this problem. And talk about the overlap gap property that this problem indeed does exhibit. And intriguingly exhibits it in the right place, somewhere between here and here. Okay? To summarize, global optimum is given by this expression. Best found algorithmically is a little bit lower. Something is happening in between. What is it? To formalize the phase transition property that I'm about to describe, let's do the following. You pick a parameter alpha between 4/3 and √2. So some parameter here. This is supposed to indicate the target value of the matrix you would like to get. Right? So specifically, now look at all matrices and pick any 2 matrices C1 and C2 with average value equal to alpha times this default value achievable by the first two algorithms. Okay? Now, we know such matrices do exist because all the way up to √2 they do exist by the optimality analysis. And when alpha is equal to 1, these matrices are achieved by the first two algorithms. When alpha is equal to 4/3, it's achieved by the new algorithm that I just described. So we pick alpha. In fact, let's pick alpha all the way from 1 to √2. I made a mistake. We will consider the whole full range. So what do we do then? Then we do a fairly simple thing. It's a little bit of work, but it's not too complicated. We'll look at the expected number of pairs of matrices which A, achieve that average value, and B, they have a prescribed number of common rows and common columns. So we fixed parameters now, 2 other parameters, y1 and y2, and ask ourselves, what is the expected number of matrices that have this average value and have y1k common rows and y2k common columns? And compute it. And that can be done. That's not too complicated. And the leading term is the expected number of such thing is given by this expression. So it's exponent of the scale is k log n, and the leading order term is given by this expression. It involves y1, y2, and alpha. Questions? Is it clear? Okay. But now notice is that when f, this parameter, is negative, if it so happens to be negative, that expectation goes to 0. And therefore, such matrices simply do not exist with high probability. That's kind of a moment argument. And if it's positive, this expectation goes to infinity, then you have to use the concentration argument to show that in fact such matrices do exist. So what I want to do next is to plot this function, and specifically indicate when it's positive and when it's negative. And then we will see that there's actually 2 phase transition. One is non-interesting, I'll go through that really fast, and one is interesting, I'll go through that somewhat slower. First phase transition happens at √3 over √2. So as long as alpha less than this quantity, it turns out that all the values of f are positive. So here we fixed alpha and go over all pairs of y1 and y2. And it turns out that all such values are positive. So the redness indicates how large is the value, and yellow indicates how low is the value, but they're all positive. So all such pairs are achievable. If you go above this threshold, then you have these white regions. These are the regions that represent where the function f is negative, and that means that such matrices do not exist. In particular, for example, if you take point 0.9 and 0.1, it means that you cannot find two matrices such that have 90% common rows and 10% common columns and achieve the target value. Right? Such things do not exist. And that otherwise the region sort of looks like this. And that picture continues up until 1.3, this numeric value, which is actually explicitly given by this expression. It includes 4/3, so it's somewhere here. So alpha critical now is 5/3 over 2 over 3. And what's happening at 5/3 at this number is that this region becomes disconnected. So you go a little bit above this region, and then you see this picture. You see this picture, that there is a separation between such pairs of matrices, and what it means is that when you have two such matrices, either have quote-unquote a lot of common rows and common columns, or, no, a lot would be here, or few, but there is a region in between that's not achievable. And somewhat intriguingly, this happens above the threshold we achieved, not exactly, but above the threshold, but below, strictly below the global optimality. So, guided from similar things that we observe for other constraint satisfaction problem, one would guess that perhaps this is the region of hardness. This problem is hard to do in this regime. Questions? Why do we believe? Why is it reasonable to believe that that these problems are hard in this regime? There's no proof of that. We can't prove that. We can't prove that the clique is hard on average. That would be great to have something like this. At least what we can do is that we can, when we observe such separation in sparse random graphs, at least we know that certain classes of algorithms, like local algorithms, appropriately defined, that would be a different talk to discuss that, but certain class of so-called local algorithms provably cannot overcome this connectivity threshold. Anytime you have the overlap gap property, the local algorithms cannot overcome that. And that's something you can do for sparse graphs. So in this couple of papers, this was done for the problem of largest independent set in sparse random graphs. And also in a different sequential version motivated by the questions of analysis of certain algorithm proposed by physicists, survey propagation. This can be done also for not all equal k-set problem. So I'm almost out of time. 3 minutes. So I have some remarks here, and I could go through that. But let me, in lieu of that, and you can. Okay, so you have a choice: either read the remarks or listen to me. I want to, or both, if you can do multitasking. I want to go back to cliques for a moment. Cliques in dense graphs. And now, in light of this, or in the light of whatever we know for sparse graphs, one can ask, in 2 log n versus log n question, algorithms, existential versus algorithms, what explains this log n threshold? What can tell us? Is there some phase transition that tells us that at log n something interesting happens? We can't prove so far such a phase transition, but I'll give you a conjecture that we can partially prove, and perhaps it can be fully proven. So the conjecture is as follows. So I'll describe it somewhat loosely, but hopefully that's good enough. fix m click, where m is certain parameter, of the size a little bit above, of the size alpha log n. So instead of, we did two matrices, now we have m clicks. And alpha, whether it's alpha less than 1 and alpha bigger than 1, that's where we want to see some phase transition. And then let's do the following. Let's fix 2 to the m possible intersections of this graph. So fix any subset of indicators for these clicks, and look at the intersection of these clicks, and look at their cardinality. Okay? That gives you a vector let me describe differently, perhaps, xs, where s is a subset m, of such cardinalities. Look at those which are so look at those which are achievable by clicks, and now draw a 2 to the m dimensional subset of 2 to the m dimensional cube, where you put a dot wherever this point is achieved and wherever this point is not achieved. So some region is achieved here, another maybe region achieved, and something like this. So the conjecture is that that region is disconnected in this case, and sorry for this reverse, and connected here. So the transition from easiness to hardness, the onset of the transition from easy to hard problems happens whenever this region of overlaps breaks down into disconnected components. I think we can prove that it's connected when alpha is less than 1. We can definitely prove that it's disconnected when alpha is bigger than 1 over root 2, because in that case it's disconnected even when m is equal to 2. But presumably, and in fact provably, you can improve it by m going to 3, that goes down. So the conjecture is that by taking m large enough, you can take it as close to 1 as you can, as you want. But that we can do. I'll stop here.
Good time for questions?
Can I ask if instead of maximum, is it known what is average size of click in GNP?
Average size of click in GNP? Yeah, just, yeah.
If by chance this I don't know, just this greedy algorithm wouldn't it somehow produce average size?
I see. I'm not sure. I think because very few. Yeah,
So one. Probably. I mean.
Yeah, you have to do, but I because there's too few of the larger ones to actually contribute. Yeah, but then you can do, you can do the partition function. You can say lambda to the cardinality. But then you can tune lambda to be anywhere from 1 to the largest click. So, but I don't think it's going to be described by just average value.
Very few of the largest.
Well, if you take absolute largest, there is actually typically sort of 1 or 2, literally very few of them.
What you wanted to ask of the average size of those that you cannot locally improve. That would be analog of.
Okay.
But then you will get into something like you would have the separations. Yeah.
Do you have upper bounds on the quality of the approximation of the different algorithms you proposed for the submatrix? Because I was thinking that you can reiterate the algorithm to obtain better results.
For the algorithms that we analyze, we know their performance, so we don't need bounds.
Okay, but the question is, if, for example, you know the expected size, maybe by repeating the algorithm from different starting points, you can get something better. I don't know if...
No bounds. I mean, presumably, if you rerun this, let's say, iterative search procedure gazillion times, you'll get to optimality. So you have to somehow So you would have to ask, okay, suppose I restarted polynomially many times. I'm not sure, well, even the vanilla version was hard to analyze. This would be even harder, but I don't think it will give an improvement because things are very concentrated, super polynomially concentrated. So even if you restart it polynomially many times, it won't give you anything. In anticipation, but we haven't done the analysis.
Anybody else? Okay, thanks again.